About images. The methods that I'm going to show you, of course, the overall classification method can be applied to feature vectors from all sorts of things. And in fact, if you take a machine learning class, many of you already have, you've learned about discriminative classification for arbitrary vectors. So we'll spend a little bit of time talking about features that come from a computer vision or an image element, right? So you wouldn't use them for biological data of describing genomes, but the representation you might apply to other kinds of pictures. So you have to build that model, and the second thing you have to do is you have to train the classifier. Then, when you run this thing, what you have to do is you have to figure out, I need to generate new candidates to test. So I give you a picture. What does it mean to say, tell me, what's in it? Is it the whole picture, parts of the picture? We'll talk about that in a minute. And then once I generate candidates, I'm going to have to score them. I have to evaluate them with the classifier of yay or nay. For computer vision object recognition, we're inherently interested in finding objects in images, okay? And that finding means essentially two parts, or they're sometimes combined. There's this notion of detection and labeling, right? So here on this picture of, person standing next to a car, I have to not only sort of say what's in it, I have to say, oh, okay, over here, and I'll draw a box, because a lot of these things are window-based, saying, okay, that's the car, and by the way, over here, that's the person. So in general, that's what you have to do, and the most common approach to doing that is referred to as windowing methods, all right? So there are lots of different ways of thinking about windows. We can start by thinking about sort of whole images, right? So here I have a picture of a couple of training examples of koalas and a couple of training examples of pandas. This slide, borrowed from Kristen Graham. Kristen has a thing for cuddly folks with big ears. So if any of you are cuddly with big ears, you can give Kristen a call. I hope Kristen's okay with that. So, clearly, here I have my koalas. We've talked about koalas before, how they're not bears, right? That koalas are this thing. And here we have pandas, which are bears but are just mean. Anyway, and what we'd like to do is we'd like to somehow learn a way of discriminating between them and say, which ones are which. So one way of doing this would be to just build some sort of a holistic description of the entire picture with the assumption, we'll get to this part later, that the picture thing that I'm looking at is mostly the koala or mostly the panda. So what would be the simplest possible description? Well, here's one. How about I just build a histogram of the pixel colors? Now I'm showing it here as a single image, so it's black and white. You could do this in RGB and you'd essentially have 3 histograms. And you could imagine that basically you could try to determine that, these things look kind of pretty much different than this, so that might be a good descriptor to try to find where the boundary might be. You might try something even simpler. I don't know if it's simple. Yeah, I guess it's simpler. It's not a very good idea, all right? The same way we did in PCA, you can take all the little pixels, put them in a great big vector space, and you could say, okay, here are a whole bunch of koalas, here are a bunch of pandas, find me the boundary. Do you think that would work well, or do you think that would not work well? What do you think, Megan? You think it would work well?
No.
No. Okay. One of the problems is, if I shift the picture just a little bit, all those pixels move around in that feature vector. So a small change in the image is going to give me a large change in my feature vector, which is not something you want to have if you're going to have a good ability to discriminate between them. So that won't work. And what about the color thing? Well, you think if I just did that color and intensity thing, that would work pretty well?
No.
No! Okay, look, suppose I make it brighter today, or there's a shadow being cast upon the thing, etc., whatever. I get major variations in sort of the distribution of the intensities, okay? Do you remember when we were talking about trying to do tracking or trying to find things, motion? We were looking for what were called interest points. I hope you remember that, okay? And you remember interest points, Harris features, those kind of things, they were based on the idea of places where you had high gradients. Okay? In particular, those were where you had variations in the direction of the gradient as well. And the idea was that gradients' corners were quite robust with respect to changes in illumination. So if we take our koalas and our pandas, we can consider sort of edges, contours, the idea of these intensity gradients, right? Those things tend to sort of stay where they are in terms of, if I change the intensity. Right? But of course, we do have this problem that as I move the image just a little bit, I might get shifts in the location of where those pixels are. So now, you remember SIFT features? So we did the whole thing with SIFT features, which took histograms of the orientation, and we computed these little feature vectors, right? Well, here, imagine taking your picture and you just cut it up into, say, 4 quadrants, right? It's easier, right? So 1, 2, 3, 4. And I suppose I just compute some histograms of the orientations of the gradients in each of those regions. And I do that for each of these pictures, okay? It's robust with respect to illumination changes because the gradient's there. Is it robust with respect to small shifts in the picture? Megan, yes or no?
Yes.
Yes, it is. So the reason that it's robust with respect to these small changes is that, you know, if I move this guy's ear a little bit around, you know, a bunch of pixels, the distribution of the gradients is in that quadrant is going to remain about the same. That's why down here it says locally orderless. What it means is that I'm not worried about exactly which pixel you're in. I've got a general distribution in 1 or 2 different areas of the image, okay? We're going to talk a little bit more about this, but basically what I just talked about, for example, whether you're doing the whole histogram, of the whole image, which doesn't work very well, but you could do it, or if you build like these orientations of gradients in each of the quadrants, you're building a model, a description of that instance. Oh, by the way, you take for each of those histograms of 4, and you just string them into one great big feature vector. That's your description. So now what you have to do is you have to train, or sometimes referred to as learn, a classifier. Given a bunch of those feature vectors describing koalas, and given a bunch of them describing pandas, figure out how to discriminate one from the other. So here's the basic description. All right, so let's suppose we're trying to learn cars versus not cars. So how many classes is that?
2.
Sorry, how many classes are that? How many is that? It is 6. There are 6 classes, but the number of classes is 6. Actually, the number of classes is 2. I don't know. It's called a binary classifier because there are 2 classes. So, for example, suppose I have a little picture here of a car, and I have to decide, is it a car? And what do you think? You think that's a car?
Yes.
Good, she got it right. Yes, it's a car. Okay? Now, here's another picture. Okay? Taken somewhere in China, I think. I don't remember where. Sorry. So is that a car or not a car?
No.
No. Very good. What we need are methods of doing that. Now, there's been a huge effort in machine learning and applied to computer vision over the last really 15, 20 years of methods of doing discriminative classification. What you see listed here are a whole bunch of methods, a couple of references below them, of how to go about doing that. We're going to talk about 3 of them. I've just highlighted them here: nearest neighbor, SVMs, boosting. There are others as well. The general approach, and there's a huge literature on this now, especially with these large-scale object recognition competitions, of what's the best feature vector you can use, learning different feature vectors, sparse representations, a bunch of other things, and then, given those representations, what are the methods that you should use to make the classification. Here are the 3 that we're going to talk about. If you take more machine learning, just remember later, you could apply those methods to those other representations. Our fundamental assumption is going to be someone, and hopefully that's somebody you don't have to pay, but somebody is going to give you a database of lots of examples of the things you want to find and lots of examples of the things you don't want to find, and then you're going to train the classifier. Now, once you do that, you have to come up with some way of given some new image, how do you test it? So you remember we talked about you have to generate these new candidates and you have to score them. So here's the basic idea. You start off with a window, and Kristen is really good at this animation, right? And you might take that window of a particular size and you scan it all over. And what you do is you apply your car, non-car classifier to every one of those windows. And you say, do I see any cars? Do I see any cars? Do I see any cars? Not very clever, but it just works very well, right? Because the classifiers are quick and they're accurate. So as opposed to having a different way of trying to do detection versus labeling, I basically do detection by labeling. There is a problem, of course, though. I picked a window. Well, suppose I'm nearer to a car. Does the picture of the car get bigger or smaller? That one's an easy one, Megan. If I get bigger, does it look bigger or smaller?
Bigger.
Bigger, very good. So what do I have to do? Well, I just have to try bigger windows, and I slide those all over the place. And if this feels kind of data intensive, you're right, and there are various tricks to doing it, but that's the general idea, is that you take these different size windows and you apply them to different places in the image. Taking a little breather here just to remind you what we're doing. So we have this, basically we're doing window-based object detection, right? The training, we basically see it says obtain training data, doesn't say how. You just hopefully can go to the web, or like I said, you pay somebody to click on things, because you can do that these days. You define some features, so you have to figure out what it is you're going to measure about it, and then you're going to train a classifier, and that's what's shown here. So I take my windows, and I have positives and negatives. That comes from this great big set of training examples, and you see over here on the left I've got these cars, and over on the right you've got these non-cars. So the idea is you use those training examples, you extract the features, and then you train your car versus non-car classifier. At testing time, what you do is you're going to take your new image, and you're going to take this window and you're going to slide it all over until hopefully you land over here and you classify it as a car. What about those discriminative methods we were talking about? As we said before, they find a division, a surface between the classes. We're going to talk about a couple of different methods. The one I want to talk about today is nearest neighbors, and then we'll do separate lessons for each of the other two. So the simplest method we're going to talk about is nearest neighbor classification. And it is a discriminative method because we are using the boundaries between, I won't say classes, I'll say examples, right? The boundary is always between examples of the classes. But we actually don't have to do very much training. So the idea is we have some feature space here labeled as blank. It should be X1 and X2. This picture, by the way, is taken from a classic book, Do to Heart. The original one is Do to Heart. The new version is Do to Heart and Stork. And it's a good way of learning sort of classical pattern recognition. So the idea is I've got a bunch of examples. The negatives, so the not A's, are these little black points here, so the black thing. And then I've got some positive examples, right? And those are the little red ones there. And when I come up with a new point, all right, so there it is in the green, basically that's my new novel test example. And how am I going to label that? I'm going to find the closest training example. So in this particular case, the closest training example is that one. And so I say, aha, the closest one is a positive, so I'm going to label this new one a positive. All right. Now, drawn on this picture actually are the divisions themselves, and the computer scientists among you will recognize that as a Voronoi partitioning. Right? When you partition a space using a Voronoi method, you essentially carve the space up into these little chunks, where this chunk means that if you're in that chunk, this black point is the closest one to you. And so all nearest neighbor is doing is giving you a Voronoi partitioning of the space. It's, shall we say, pretty easy to implement. It has a couple of problems. One is it doesn't work very well. We'll get to that in a second. It's also very data intensive in terms of the memory of what you need to know, right? So if I give you 1 million training examples, how many of them do you have to remember, Megan?
1 million.
1 million, that's exactly right. Furthermore, every time a new point comes in, I got to find the closest one. So if I was really dumb, you know, I don't have a master's computer science degree from Georgia, I might go through them, all of them one at a time. If I'm a little smarter, I'll use something called a KD tree or some other hierarchical representation. But you're still searching through a lot of these things. So at test time, it's very painful as well. So not only is there a lot of memory stored, etc. But let's get back to that doesn't work all that well thing. Well, one of the things that might happen is that I might have, you know, an occasional kind of spurious point, or I might be in an area where I really don't have too many points nearby. And what I'd like to do is be able to make a more robust decision. Okay? And the way of doing that is referred to as KNN, or K nearest neighbor. And it's really very simple. It's basically the idea, if I've got some new point and it's written here as an X, so that point right there, I don't just find the nearest point. You got to think like a computer scientist. You find K. So K might be 1, it might be 3, it might be 5, it might be 7. Whatever choice you choose to make, you would look for K. So in KNN and 5NN, for example, you know, if I have this point X, okay, what I'm going to do is I'm going to look for the 5 nearest neighbors, right? And I'll just 1, 2, 3, 4, 5, okay? And in this particular case, 3 of them are black, 2 of them are red. Black is negative, red is positive, so I would classify it as what?